So good morning, everyone. Welcome to our talk about load balancing. My name is Murali Suriar, and this is Laura Nolan.
I'm Laura Nolan. You may remember me from such talks as 1 hour ago.
So we work together at Google. Laura is now working at Slack. We spent some time doing load balancing things, and we'd like to talk to you about it. Why do we want to talk about this? Because we've spent a lot of time doing this in our careers, and because load balancing failures often end up looking like dropped requests and bad user experience. Just a caveat up front, this is going to be a super accelerated talk. Our apologies ahead of time if we skip through slides, but we will be publishing the slides, and they all have lots and lots of links for people to go and read more background information. So with that being said.
Yeah. Okay, so imagine the simplest possible site. So it's the late 1990s, the .com boom is in full swing, and to compete with pets.com, you have an amazing owl merchandise site called superbowls.com. This will be our template for the rest of this talk. So we got some end users, and through some magic, their requests are hitting our superbowls.com, which is, for the purposes of this talk, this is a magically horizontally scalable application. If you want to know more about that, I highly recommend Martin Kleppmann's data-intensive applications. Otherwise, we're going to skim entirely over the how do you scale your application part. So, again, simplest possible thing. We've got DNS. We've got an A record. It's pointing from superbowls.com to our single LAMP stack at a publicly routable IP address, 203.0.113.20. Requests go through the intranet, as is customary, and we're in a colo somewhere. It's got a couple of edge routers. They're advertising a subnet containing that IP address out to the intranet, where magic takes place. Okay, so this is okay. If we get slash dotted, it's not scalable, right? We've only got one server. So we don't really have a great amount of load distribution or high availability. We have a little bit in the network infrastructure, and we're going to talk a bit in a little while about how that works. But there are many, many, many elements of load balancing that we do not have here, okay?
So the first thing we probably want to do is we want to be able to have more than a single machine serve requests from this thing, right? Like, let's assume for argument's sake that we have written possibly the not most efficient LAMP stack in the history of the world, and each server can only serve 5 requests a second. We want to be able to serve more than 5 requests a second, and so we want to add another server. And a very common way to do this when you're going from one machine to multiple machines is you buy another machine, you put it in the same rack as your first machine, you give it probably the next IP along from your first IP address, and then you update your DNS server to, instead of returning just one IP address when people look up superbowls.com, instead they get 2 IP addresses back. And we're going to hand wave over the implementation details, like DNS client behavior is a whole other talk in and of itself, but if you're lucky, you will probably get about 50%, a 50-50 split of incoming requests between server 1 and server 2, hopefully. So then the question becomes, okay, what happens if one of these servers goes away? So in our previous design, if your one server went away, then your site was down, and this was not great. In this design, if one server goes away, then about 50% of your clients, again, hand-waving the details of like where the load's coming from and how it's split, but about 50% of your clients are going to get timeouts. Probably someone tweets at you, unless you've thought ahead of time and set up monitoring. And you're like, okay, that server's broken. Let me update my DNS config and remove .21 from my pool of 2 things that I can return. You mess around with bind and you FTP a file somewhere and then restart your DNS server. And after some amount of time, your users are no longer seeing timeouts. But it's probably fairly clunky. A brief aside about DNS load balancing generally. So DNS has this concept of TTL, right? Time to live. This is basically when you get an answer for a DNS query, how long is that answer valid for? How long should that client hold on to that answer before it asks for, what's the updated state of the world? And there's a trade-off here, right? You can have a very long TTL. You can set it to, say, a day. And the upside of this is there's not a great deal of load on your DNS infrastructure. The downside is if you have a failure and someone has already visited your let's say they've visited your website before their morning coffee and then they want to look at some superb owls over lunch, if you've had a failure in the interim, they're just going to look at the old result, and that old result may be still pointing to a broken server. With short TTLs, you have much higher load on your DNS infrastructure. There's more latency because you've got a network round trip to do your DNS lookup. And also your DNS availability becomes a much bigger overall proportion of your overall reliability. And a lot of clients will ignore very, very short TTLs anyway, right? People will set 5 or 10 seconds, but many clients will ignore stuff lower than like 1 minute or 5 minutes. So back to our story. This gives us some load distribution, right? It lets us distribute load across multiple pieces of physical infrastructure. There's not really a story at the moment for how do we avoid unhealthy infrastructure, right? We described you notice it's down because someone complains at you. Most DNS servers can't talk to your actual serving backends themselves, so they can't do anything that resembles health checking, and they're not really load aware, right? They don't know that server 1 is twice as busy as server 2, and so they can't adapt their balancing equivalently. It's also very, very complicated, right? You're relying on a very complex stack, your DNS server, DNS load balancing, geo load balancing, what your clients are doing. And to be clear, right, DNS wasn't designed as a load balancing solution. It's just what people use because it's there and everyone kind of uses it as their initial kind of API for finding a service.
Okay, so back to our system. So we've seen the shortcomings of DNS load balancing, and we've decided that we would like to do better. So what we're going to do now is we're going to put a layer 4 load balancer. That's our little friend here, the black icon with the three arrows. This represents one or a cluster of network load balancers. The idea here is to give us more control. So fundamentally, what this layer 4 load balancer is doing is it's presenting a virtual IP for our service to the outside world. This virtual IP is our 2030.113.200. So we're advertising that to the outside world, and we're using that's what we set our DNS to point to. But now our 2 servers that are actually serving the site are inside of our private IP space. So what happens is when we get a request in through the internet, crossing our edge routers, they're going to send the packets to the layer 4 balancer. And the layer 4 balancer is going to balance the TCP connections, or UDP connections, potentially, to our backends. So this is connection-based. This isn't smart. This doesn't know about your cookies or your HTTP headers. This is just seeing packets. So how this works is it's going to be this thing called a 5 tuple, or it can be less than 5 depending on the protocol. So what you do is you take your source address and port, destination address and port, and your protocol, and you hash that to get one number, and then based on that number, you pick a backend. So the big idea here, and this same idea is used in a lot of places wherever we see load balancing at the network there. And the big point is we want packets that are in the same TCP connection to take the same path. Because if that doesn't happen, you get a lot of out-of-order TCP packets, and that makes TCP pretty unhappy and perform pretty badly. So there's no point doing that. So we want everything to take the same path. We're balancing connections. So this gives us a lot more power than we used to have. I should also say that layer 4 balancers can do smarter things than this.
Yep.
All right. Our layer 4 balancers can be smarter than this. Some of them, like Google's maglev and Facebook's Catran, they can do a consistent hashing technique, and the idea here is deal with failure in a more graceful way. So if one of our load balancers fails, we still see most of our connections not getting reset. The Google maglev paper is a really good read on this. So another thing that people very often do is they say, we can be smarter than just doing round robin or the kind of hashing technique. What we can do is we can load balance connections onto the currently least loaded backend. We advise caution in this because that's a great way to DOS a new backend that just came up. But this gives us a ton of power. So now, without any TTL issues, we can add new servers to our pool. We can remove a misbehaving server from our pool. The layer 4 balancer is right in the serving path. So it's going to be aware immediately if one of the backends stops responding. So it's very easy to build a health check in here, unlike with DNS, which is not in the serving path. So this is a really big step forward in terms of our reliability. So now we have a good story for load distribution, high availability, and flexibility. But this is not the full story, as we shall see. So one thing, we're going to digress for a moment. We're hiding quite a lot of network detail in these big chunky arrows. So we alluded to before, there's quite a lot of load distribution happening at the network there. And understanding how that works is pretty fundamental to understanding how things work in the overall ecosystem. So we're going to digress and talk about that for a little bit.
Okay, so what we're going to be talking about here is how do hardware network devices forward IP packets, right? So talking about your network routers, switches made by big network vendors. Typically they will be in a data center. They will be managed most of the time by a dedicated network team. In our diagrams, the round things, the circles with the 4 arrows on top, are routers. And when I say a router, I mean something that's looking at primarily the IP portion of a packet. And the rectangular things are switches, and by that I mean stuff that's looking at the Ethernet or MAC address layer of a frame. Basic things to consider. In networking, 1+1 redundancy is very, very common for a multitude of reasons that we won't get into in this talk. But let's start with just talking about a server in a rack. So we have, in this case, 2 racks. Each rack has 1 switch, and we're just going to talk about this one server on the left-hand side. And so the way that we get high availability out of this, right? So you have 2 routers coming into, let's say, this data center. There are umpteen racks. We draw 2, but there could be 200. Every rack is uplinked to both routers. Every server is connected to the 1 rack switch in its rack. So if you lose the rack switch, you lose the rack, but that's okay. Switches are pretty reliable. But what if you and in steady state, your inbound packets come in via some path, and they go out via one router or the other. And the typical way to do this, for the inbound path, you do something called IP multipath. Again, network digression, not really relevant. And on the server side, to send traffic out, you will use a protocol that looks, basically does like a health check and a keep alive between the 2 routers. A common one is VRRP, a vendor-specific one is HSRP. These are just redundancy protocols to say, I am currently the default gateway for this rack or this subnet. So what happens if we have a broken router? If we have a broken router and it breaks cleanly, then transparently to the application, ideally, your inbound and outbound traffic just flips to the other path, right? Your VRRP address moves over to the other interface. Your routing protocol, BGP or OSPF or whatever, in the wider data center, then flips to, oh, that router 1 has gone away. I will send traffic to this rack to router 2 instead.
Okay. Yeah, so that's how we deal with failure. How do we deal with actually using the capacity that's available to us? So let's imagine that we have racks full of machines. Each machine has got multiple uplinks, and each switch has got multiple uplinks. It'll be nice to be able to use more than one of those parallel paths. So this is capacity. So there's lots of ways of distributing load. So ECMP, equal cost multipath, weighted multipath, link aggregation, which is where we sort of bundle multiple parallel links into one logical link. But they have a lot of stuff in common, so they tend to work in that same way using the hash of the 5 tuple that I mentioned earlier. And they're stateless. You're not storing anything per connection. So this is kind of how it looks capacity-wise. You'll see, different connections are using different paths. We can use, connections that are coming from one box can take multiple paths to the outside world or to different destinations. There are some caveats here. So all of these techniques, they rely on being able to probabilistically balance lots of fairly small flows across redundant links. Where these things tend to fall down is where you get things like elephant flows, which is where somebody says, hey, I want to copy gigs of VM state across to another place in a really, really short period of time across one connection. You're going to have a bad time because you're going to overflow the capacity of any of these individual links in our parallel setup, and that limits the overall capacity that's available to the parallel link setup. How it does this depends on the implementation, but generally speaking, bad news. So this is the diagram that we had before. So we've talked about multipathing and load distribution, and we're going to go back to talking about network load balancing now. So let's talk about the two ways that we can implement our network load balancing. So first way is transparent proxy. So packets come in, they hit our layer 4 balancer, and the layer 4 balancer starts a new connection to a backend. Basically, we're doing network address translation here. And what happens here is that our balancer needs to maintain state so it knows where to send the packets back to the originating client. There's another couple of downsides here in that the backend service won't actually see the IP of the original client. This can be problematic for some applications. So,
So I'm going to gloss over the implementation details here. The other general way of doing this, instead of this proxy setup where all traffic is going in and back out through your network load balancer, is something you'll hear called DSR, direct service or server return. And the fundamental idea here is you have your inbound traffic go through your load balancer. The load balancer picks for this request, well, actually for this connection, I'm going to use this backend. But then the backend will respond directly, not going back through the load balancer. And this gives you a few useful properties. One is that it means that you can have fewer load balancers because most of the time, incoming request load is much smaller bandwidth-wise than the response load, right? There are exceptions, but for most web apps, this is true. And so you can have significantly fewer load balancers in this setup. The other thing here is that with some trickery, and there are papers from Facebook, Google, and others about how to do this, you can do a stateless, kind of semi-stateless function on this load balancer, but you can have high availability because you have many of them doing the same operation. And so you can flail over from one to the other and have it be transparent to users. The third thing that is very common here is you will often try and preserve the original IP address information from the request so that it gets transparently forwarded through to the backends, and they can then use that information for like spam and abuse, IP reputation type stuff. I'm now going to gloss over like 4 slides. One way of doing this is Ethernet trickery. I don't do Ethernet trickery because it's the year 2019. Another way of doing this is what's called layer 3 DSR, and this uses IP and IP trickery, which is a much better brand of trickery. And then there are many slides talking through exactly what the packet flow is, but please read them at your leisure because we don't have time to talk about them. Right.
Okay, right, so superbowls.com, it's become big business. Everyone loves owls. Harry Potter came out. It's a big deal. Our business owners, they want more reliability. They want to go multi-region. How are we going to do this? Okay, so one way that we can do this is just by take our virtual IP that we have, our 113.200, and we can advertise that in multiple regions. And we can use trickery of the internet called Anycast to mostly have people's packets go to the closest site. So this is not too bad. It mostly works. It has a couple of downsides. So first off, like I say, internet trickery. Closest in internet terms means what is cheapest for my ISP. It doesn't actually mean geographically close to you. Most of the time it does, but not always. So that's one thing. Another thing is this Anycast technique. The way that our load is being spread, it's based on sort of the vagaries of where are my users and what's happening in terms of ISP internet routing on the wider internet. So we can have some problems. So Murali has an entire talk on this from a couple of years back, and the slides are linked at the end of here. But basically, you can't control it. You can't control where your traffic's going. Monitoring is hard because you can probe it, but you don't know which instance you're probing. And cascading failure is easy because, like I said, we've got no control over how much traffic is going where. So if one of these instances goes down, traffic will just flow to another one sort of, from your point of view, almost arbitrarily. So you can have all your sites knocked down like dominoes by a cascade of traffic. This is not good. So new plan, no Anycast. We've got a different VIP per data center, virtual IP per data center. And we're back to our old DNS setup again. So we're using DNS to control how traffic goes between the two of them. Now we're back to basically the same problems we had earlier, exactly the same. It's very hard. We have all these delays if we want to stop sending traffic to one particular site. Also, we might have an installation right next door to a user, but we could be routing them to our servers thousands of miles away. So we could be introducing extra latency, which is not good either. So here's a way that we can solve the problem. We have an IP, a primary IP for each region. We advertise both IPs in each place, but we advertise each IP at a higher priority in one location. We can use BGP trickery to advertise something, but in a less preferred way. So it becomes a backup if the primary instance goes away, but it's not going to route traffic in the normal sense. And then we use a trick where we make our DNS server try and figure out where is the user coming from and route to the nearest, and not nearest in ISP cheapest terms, but actually the nearest installation.
Yep. So the technique Laura referred to is DNS geo load balancing, or GeoIP. There are many terms, but it's basically look at an IP address, try and work out where it is. There are many problems with this, primarily that the internet addressing scheme wasn't designed to deal with this many years ago, and it definitely doesn't deal with this now, particularly with IPv4. IP addresses are kind of scattered all over the internet, and it's just very annoying to work out what IP address physically lives where and topologically where it is in relation to where your serving infrastructure is. It's very manual, it's very error prone. The other big thing is it's fairly common for large internet service providers to have one or two DNS servers behind which their entire user population lives. And if you think that's like a national carrier in, say, the US, West Coast users and East Coast users will have very different profiles as regards like where's the closest thing that you should serve them from. And so there's lots of room for error here. There is a way to fix this. eDNS client subnet is the thing you should Google. There is an RFC 7871, which is, I think, draft, but a lot of things implement it now. But back to our main story.
So, yeah, DNS geo load balancing.
Yep.
It sucks, but it's basically the best thing that we have, unless you've got very significant client control. So we've seen how we can have low distribution, high availability, flexibility, geo-awareness, but there are still some things that we can't do. Sometimes a request is not identical to another request. We can have very big, heavyweight, large requests and small ones. We also sometimes want to be able to do content-based balancing, so we would like to balance based on a cookie or based on, say, a parameter in an RPC, or what kind, are you a high priority or a low priority customer, that kind of thing. We have no way of doing this yet. And we also don't really have a great point where we can implement complex rules for rate limiting and load shedding and that kind of policy stuff.
So this generically is called layer 7 load balancing or application load balancing, or you may, in web terms, you may hear this called a reverse proxy. The basic premise here is if you think back to our previous diagram, or in fact this diagram, whereas before you had a network load balancer, right? This black square is a thing that's just looking at IP packets. In an application proxy world, it is actually a server that knows how to speak the protocol that your clients speak, right? So in a web environment, it's a web server. In an RPC environment, it knows how to speak gRPC or whatever RPC protocol you're using. And then it has knowledge and information on what properties of that request are relevant for balancing, right? This RPC is more expensive than this RPC. Queries to this hostname should be sent over here rather than queries to this hostname should be sent over here. So it gives you a lot more flexibility and a lot more expressiveness in the way that you can do your load balancing and your traffic routing. The other thing here is we're talking about this as though you would just switch from one to the other, right? So you go from a network load balancer to an application load balancer. One thing to bear in mind, this is more expensive, right? Application load balancing typically has to be done on a real CPU with some small amount of RAM per connection, and so that's going to be fundamentally more expensive than something that's just doing network packet inspection in silicon. And so if you get above a certain scale, a fairly common pattern is to take the layer 4 network load balancer you had before and have the backends of that be these application load balancers, which are doing like still fairly lightweight calculations versus actually serving the responses to the request, but it gives you these different layers at which you can tweak different aspects of your load distribution, load balancing, and routing. And you can apply different policies at different levels, right? You could apply IP blocks at your layer 4 balancer, but then you could say, this particular user agent is very clearly an Internet of Things botnet, I'm just going to block that, right? So scalability. The thing with this is that this will take resources on your load balancer, right? Your application load balancer has to maintain some state for every connection, every request going through it. these balancers crashing will be seen by users. Network load balancers, you can reasonably make it as though it's transparent to users in a lot of cases. But the layer 7 balancers also give you more power, right? They can retry autonomously and hide that from the backend, right? So if you hit a layer 7 balancer and the first backend it tries is dead, it can just try another one and just leave your connection open longer, and you see a slower response, but you don't see a failure. They can also be load aware. They can do rate limiting and load shedding, right? Because they speak your application protocol, they can get more information about the health state of your backend and the load state of your backends. And you can do things like rate limit per user, per URL, right? Maybe serving this JavaScript is less relevant than actually serving the actual core content of the page, that kind of stuff. And so you can have flexibility in how you respond to overload events and DOS attacks and stuff like that.
Okay, load balancing algorithms. Now this could easily be 30 minutes just on this slide. But very, very briefly, round robin is, we talked about stateless hashing before. Round robin is a really common one. It doesn't have any catastrophic failure modes. That's great. We talked about least loaded and how that can lead to essentially doing a self DDoS on a new instance or something. It can also lead to something that's serving errors, attracting a lot of traffic because serving errors is cheap. Weighted round robin is something that you can do if you've got backend servers that have, varying amounts of capacity or maybe just less antagonistic neighbors. You can look at over time which backends are performing well, less errors, less latency, and you can you can increase the weight of those in your round robin. Probation, this is a slow ramp up for anything that's new. Choice of two. Choice of two is a sort of a very efficient algorithm. I think it came from Netflix, some work that they did last year. You pick two backends in your pool and you send to the one that looks best in terms of errors and latency. So this is efficient to implement and it lets you prefer better performing servers without leading to the thundering herd DDoS effect. Okay.
Yep.
Yeah, we'll move on.
Move on.
So very quickly, a couple of words on client load balancing. So client load balancing is another technique. So instead of actually having your load balancer in the serving path, in a context where you trust and control your clients, you can have your clients sort of implement the load balancing themselves. And how this works is you have some kind of registry, which you'll see down there in the bottom right. And the registry knows about where your resources are, where your servers are. What your clients do is they query the registry to get the information they need, and then they probabilistically balance their own backend connections themselves. Now, this has some advantages. You don't need to run computationally expensive load balancers. You get to save the latency of the extra hop, and there's a bit of a reliability bump as well because you can cache the information from the registry, and that means that if your registry crashes, it can come back and not have too much of an impact on your service. The downsides are if you do not trust your clients, they can really, really mess you up. So make sure that you trust your clients and you have some way of blocking poorly performing client or poorly behaving clients if you need to. The other thing as well is, at least in the way we've drawn this diagram, you need a thick client library per programming language that you use. That's really annoying to maintain. So a lot of people started doing this thing with a sidecar pattern. So instead of having the client built in, you run a little process alongside your main program that knows how to communicate with your servers.
Which I think is, oh no. Yep. This is still you. Go for it.
So this is how it might fit in our systems architecture. So we've probably still got a layer 4 balancer or something that's sort of balancing traffic to our backend service, but our backend microservices are using this client load balancing pattern inside it. Also, service meshes are basically this, except with a sidecar.
Yep. So this is the other thing you can do to remove the need to trust your clients is you can do something called a look-aside load balancer, right? So you can have a separate process where the registry was before. In addition to it just answering queries, it also receives load reports from all of your backends, right? And so the thing that's doing the balancing is now controlled by you. Yes, you still have to trust your clients to an extent, but they're not able to change the load balancing state of the system, right? They can decide, an individual client can decide where to send load, but it can't disrupt the control aspect. So this is like a nice hybrid approach that maybe gives you some flexibility. So this setup, we assert, gives you a lot of the criteria that we talked about from the previous setups, so we'll call that great victory. I'm pretty sure Emil's going to gong me off stage in a second. So at this point, what do you want from your systems, and what constraint do you have, right? Do you want capacity, availability, or control? Do you trust your clients? Do you control your whole stack? We do not have time for questions, but there are many links in these slides that you will hopefully be able to read at your leisure. Thank you very much.